Hi guys, you're welcome back again. My name is still Timothy Morewa Joseph. In today's lesson, you're going to learn how to resolve a vector into perpendicular components. In our last lesson, we have learned about vectors as quantities with magnitude and direction, examples such as velocity, acceleration, displacement, and so on and so forth. And we also study about scalar quantities, which quantities with just only magnitude without direction, and examples include distance, mass, length, and many other examples. We also learn how to represent vectors, and we discuss about the addition and subtraction of vectors, and also how to calculate resultant force and the magnitude of vectors. So if you missed that lesson, I will advise you to watch the video on EduPage, or you look for it on Google Drive. So we are going to look at resolving a vector in perpendicular components. Resolving a vector into perpendicular components, rather. So let's begin. Okay. So you need to understand that when resolving a vector into components, we are doing the opposite to finding the resultants. Look at these two vectors here. These two vectors are perpendicular to each other. When we say perpendicular, we mean that when two lines meet at a right angle. So this is the first vector, and this is the second vector, and then they meet at a right angle here. So we say these two vectors are perpendicular to each other. Again, let's go. We usually resolve a vector into components that are perpendicular to each other. By now, you should know what perpendicular lines are. Again, I'm going to take it again. We usually resolve a vector into components that are perpendicular to each other. And I said that our perpendicular lines are lines that meet at a right angle. And of course, these two vectors are perpendicular to each other. So what do we do? So the triangle, the vector has been completed into a parallelogram, and then the diagonal has been drawn as well. Okay, all right. So here we've got vectors, the two vectors, y and x. So let me just explain this. Here, a vector v is resolved into an x component and a y component. So we have named this vector y, and we have also named this this also x, and then here we've gotten our diagonal here. So what do you need to know again? Let's look at practical applications. You're going to enjoy this lesson, just pay attention. Okay, so here we see a table. Let's look at this table. Yes, okay. Right. So just listen to the explanation. Here we see a table being pulled by a force of 50 newtons at a 30-degree angle. So this is our table here. And then a force of 15 Newton is applied to it, is being pulled at an angle of 30 degrees. So you can see vector y 25 newtons, and here we've gotten x equal to 43.3 newtons. So I'm going to explain this also. When resolved, we see that this is the same as pulling the table up with a force of 25 newtons and pulling it horizontally with a force of 43.3 newtons. So look at it here. When we resolve by calculation, we see that what we got is that when we resolve, we see that this is the same as pulling the table up with a force of 25 newtons. So when you want to pull it up, it means that you need a force of 25 newtons. And then when you want to pull it horizontally, you need a force of 43.3 newtons. What does this mean? So we can say that it would be more efficient to pull the table with a horizontal force of 50 newtons. So it is better for us to pull it with a horizontal force of 50 newtons. Let's see calculation to help you to understand this. Calculating the magnitude of the perpendicular component. So let's consider an example. If a vector of magnitude v makes an angle theta with the horizontal, then the magnitude of the components are, so just as we have here, if a vector of magnitude v, so you can see it drawn here, the magnitude v is just labeled v, and then makes an angle theta with the horizontal, then the magnitude of the components are this. So x is going to be v multiplied by cos theta, and then y equal to v sine theta. What does this mean? So if it is being pulled up, the force applied to it, it is being put up, we are going to say the y component is v sine theta, that is v sine, that is the vector times sine theta. And if the force, it is horizontal, the force applied to it, if it is horizontally applied, we are going to say that our x equal to v, which is our vector cos theta. That is, when you are pulling it horizontally, we are going to make use of cosine. And if you are applying the force vertically, we are going to make use of sine. And that is why we say v, which stands for our vector, multiplied by sine theta, that is the angle at which it is being pulled. Is this clear? Okay, let's go on. Let's see reason. Proof. Okay, proof. All right. Okay, so do I need to explain this? I think I explained this in our last lesson, but to refresh your memories again, cosine or cos theta equal to x over vy. If you remember in your trigonometric ratio, I said we have something called SOHCAHTOA. SOHCAHTOA. Do I need to write this for you guys again? Okay, I think I need to do that. Okay, so we have something we call something like this. My God. SOHCAHTOA. Okay. Okay, let's manage this little space here. So here, SOHCAHTOA, SOH. So this stands for sine theta, if you want to call it, is equal to opposites over the hypotenuse of the right angle triangle. So something like this. And then we've got CAH, which stands for cosine. So let's just call it cos equal to, or cos theta equal to, what do we have there? Adjacent of the right angle triangle over what again? That's the hypotenuse. Is that okay? I think yeah. And then tangent. So our tangent is equal to tan, let's say tan theta. Just trying to manage the space that we've got. Tan theta equal to what? Opposite over what? Correct. Adjacent, right? Is that correct? I think yes. Opposite over adjacent. Yes. Okay. So let's look at the proof here. So cos theta equal to x over v. X over v, which is our cosine. Don't forget, I said that if the force applied is horizontal, so it is cos theta that we're going to use, and you multiply it by the vector. Okay, so our cosine, which is adjacent over hypotenuse, and what is our x here? Our x is the adjacent, and then here is our hypotenuse, so that's why we've gotten this. So cos theta equal to x over v. This very simple. Okay, sine theta is equal to y over v, and then sine theta is opposite to hypotenuse. So opposite of hypotenuse. Here's the opposite. So here is the opposite, well, which is a vertical y over v. Again, that is the hypotenuse. Can you see? It's very simple. So I've explained this in the last video. So if it is being pulled horizontally, we say x equal to v cos theta, and then if it is being pulled vertically, we say y equal to v sine theta. Very simple. Okay, so let's get rid of these items, and then we'll move to the next. Let's consider some examples, or maybe just an example. So, okay. So calculating the magnitude of perpendicular components. Okay. So let's take a look at this example. I'm just going to explain. A force of 15 newtons acts on a box as shown below. What is the horizontal component of the force? What is the horizontal component of the force? So this is the diagram. You can see the vertical component and then the horizontal component, which is applied on this pretty box at an angle of 60 degrees. So let's see the solution. It's very simple. So we are going to do the both, the horizontal and then the vertical components. So the horizontal component is equal to x equal to cos theta, don't forget, and then all you need to do is just to substitute the value into the equation. So or x equal to the force Newton, so cos 60 degrees. So when you do that and you compute this, you're going to get 7.5 newtons. So simple. So that is the horizontal component. And then when you find the vertical component, which is y equal to the vector sine theta, so and then you substitute again the values into the equation. So we have y equal to 15, yes, sine 60 degree, and then we arrive at 12.99 newtons. So you can see this is quite simple. All you need to do is just to substitute your value. So I think it is going to be more efficient to pull this box at an angle of 60 degrees with a force of 15 newtons, right? As you can see, it's very simple. Yes. Okay, let's keep this. Let's keep this. You can study this by yourself. I think it's very easy now for you to calculate vertical components and then the horizontal components of any given vectors. So let's look at summary of what we have learned. Number one, if a vector of magnitude v has two perpendicular components x and y, and v makes an angle theta with the x component, then the magnitude of the components are x equal to v cos theta, just like what you can see in the diagram. So y equal to v sine theta. Guys, thank you again for watching this video. I'm sure you've gotten a lot of understanding. By now you should be able to calculate the vertical component of a vector and then the horizontal component of a vector. If you do have any questions, please just feel free to write me either on WhatsApp or on EduPage. I'm going to attend your question, but I think this video is going to help you a lot. Thank you. See you in the next lesson. Bye. Did I say goodbye? Okay, goodbye, guys. Love you all.